In this particular video, we're going to look at the problem of a ball hanging from a spring. So when the ball is hung from a vertical spring, it oscillates with an angular frequency of 20.839 radians per second and has an amplitude of 0.023 meters. So we want to know what's the maximum acceleration of the ball and where is the maximum acceleration of the ball. So I hope it's obvious that this motion is sinusoidal. So what I have here is a graph of exactly this problem. I've got the fit to the data right here, and the blue line is the fit, the points are the data, and this 0.023 is the amplitude. That is, if you were to draw a line through the midpoint of this, that would be sort of the average value of this curve. The 20.839 is omega. It's the angular frequency. This other number, negative 14.250, is the phase. I'm not going to get into that right now. And in fact, that average value is given by this right here, the 0.177. That, you know, if you mouse over, you point there, and if you do it just right, it's really close. No, it's not letting me do it. We'll go over here. That's close, but not quite there, 0.174. So somewhere in between there is where that average value is. So really, one of the take-home ideas here is that you can represent the what do you call it? The equation here is y of t is equal to a sine omega t plus some phase, or minus some phase, depending on how you like writing it, plus sort of some average value. We could call that y0 if we wanted to. So we're still not getting the question answered, so let's explain how we can answer it from this. When you have a sinusoidal type motion, what it comes down to is, well, you can look at the unit circle. You can think of it as something that's related to circular motion. In what way? Let's see if we can... That's close, not perfect, but close. So if you look at your unit circle and you look at, say, an x or y component along that unit circle, so we're here, that y component really, y of t, is given by an equation very much like this. If you wanted to get the angular velocity of, so not the angular velocity, if you wanted to get the linear velocity, the tangential velocity of that point, what would you do? Well, what you would do is you'd say, okay, there's some radius r, there's some angular velocity here, omega, and that linear velocity, or the tangential velocity, v of t, is equal to r omega. Well, really, what this a is that amplitude. So if you just take a unit circle, that amplitude is 1. If, on the other hand, you take some arbitrary sine wave, the maximum amplitude it can have occurs here, if we're talking y of t, and there. And everywhere in between, it's less than that. So that amplitude corresponds to that r. So your tangential velocity looks like this. So let's go ahead and see if that makes sense. So what we have here is we say angular frequency is 20.839 and the amplitude is 0.023. Let's go ahead and make a calculation. So 0.023 meters, and then we multiply it by 20.839 meters per second. Nope, radians per second. Let's put it into a calculator here. So Vt tangent equals 0.023 times 20.839. So that says that we should have a tangential velocity of about 0.479, roughly. Now here we probably should round it to 0.48, but we're interested in the maximum acceleration of the ball. So let's go and look here. So we're looking, is the tangential velocity as predicted by this equation the same as what we really see? So let's go ahead, and I have the velocity plotted. Notice I'm using x instead of y, but it should really be the same thing. Okay, so this is now the velocity curve. The peak of the velocity is going to be given by that amplitude. So this is a little bit different. It's 0.459 instead of what? 0.479, but it's close. It is what's given by this fit. So if you were to mouse over one of these points, if you're able to do it, let's see if we can come over. So 0.454, so on. So it's a little bit less than what was estimated. Now, interestingly enough, the velocity has roughly the same angular frequency. So 20.839 instead of actually exactly the same. So we've really nailed it in this case. Notice that the offset is 0, so the velocity oscillates between a positive value and a negative value of the same magnitude. So if we were to then guesstimate what is the angular acceleration, well, not the angular acceleration, sorry, the linear acceleration of all this, we can apply the same sort of argument. So instead of looking at y of t, we might be looking at, well, v sub y of t. So you're looking at much more or less the same thing. It's the same kind of unit circle, but instead of r now, we have v, whatever the maximum velocity is. And so now we're not looking at v of t over here. What's tangent there is the acceleration. So this would be the tangential acceleration a of t. We can use the same geometry. So if we know v of t and we want a of t, a sub t equals v sub t times omega. Or if we use this first equation twice, it looks like r omega squared. If we plug in our value, let's plug in the value we have from this graph, so 0.459. And this is now meters per second, and of course I neglected units there, meters per second. And then we put in our omega of 20.839 radians per second. The units are going to come out correctly. Let's plug those numbers in. So a sub t equals 0.459 from the graph times 20.839, and we get 9.565. So we're going to estimate that the acceleration, the tangential acceleration, is, once more, 9.565 meters per second squared. Now, let's look at the graph. So this is our velocity graph. So here we have 9.573 instead of 9.565. So it's not bad. It's close. It's giving us an order of magnitude, not just an order of magnitude estimate, but actually something a little bit better. Our sinusoid sort of overestimates maybe a little bit here as to what we're actually getting when the acceleration is calculated. Now, I want to draw your attention to a pattern here. Let's see if we can, let's do 4 graphs at a time. We're only going to see 3 of them. We're going to plot these. And ignore this other one, it's left over in a buffer. So here's our first one, our position graph. And notice what happens here. There is a subtle phase shift. So in fact, we started about at the midpoint, and now over here we start at a local minimum for our velocity, and when we go to the acceleration we start close to the midpoint again. So if this one looks like, well, sine normally starts at that midpoint and goes upwards, so this looks like a negative sine. This looks like a negative cosine, and this looks like a positive sign. We actually see that there is a clear relationship between the position, the velocity, and the acceleration in these kinds of harmonic motions. And if you do calculus, you would see that the second graph is the derivative of the first graph, and the third graph is the derivative of the second graph. So you can actually get the phases out by looking at, basically you do a phase shift of, what is it, pi over 2 in your sine in order to get to the acceleration from the velocity or the velocity from the position. So where is the maximum acceleration of the ball? Well, the maximum acceleration of the ball, so here or there, that corresponds to the endpoints of the motion. So when you've got this oscillation going on, let's go over here. So when you are, for example, all the way stretched out down there, and you're about to change direction, you've got your maximum acceleration restoring it to its earlier position. And when you're at the upper extremity up at the top, then your acceleration is pointing downward, and the acceleration in the middle of all that is going to be exactly 0. The maximum velocity, on the other hand, will be right in the middle, either going up or going down.